Embarking on a metaphorical journey to the Earth's core takes us through the various layers of our planet, each harboring its own unique characteristics and mysteries. This exploration not only reveals the complex structure of the Earth, but also offers insights into the processes that shape our world and influence life on the surface. The Earth's crust is the outermost layer of our planet, a thin, rocky shell that forms the surface where we live, explore, and thrive. Despite being the thinnest layer relative to the mantle and core, the crust holds the key to understanding much of Earth's geological history and surface processes. This outer shell is divided into two distinct types: the continental crust and the oceanic crust. The continental crust forms the landmasses and is composed primarily of granite-like rocks, which are less dense and thicker than the material of the oceanic crust. It can extend up to 70 kilometers in depth and is older than the oceanic crust, with some parts dating back about 4 billion years. The oceanic crust, on the other hand, is mainly composed of basalt, a denser and thinner type of rock. It is constantly being formed at mid-ocean ridges where tectonic plates pull apart and molten rock rises to the surface, cools, and solidifies. This process is part of the continuous cycle of plate tectonics, where new crust is created and old crust is recycled back into the mantle at subduction zones. The Earth's crust is also home to a dynamic geological environment. It is where we find mountain ranges being pushed up by the collision of tectonic plates and deep ocean trenches formed where plates converge and one is forced below the other. Earthquakes and volcanic activity are primarily phenomena of the crust, driven by the movements of the plates and the activity beneath them. Apart from its geological significance, the crust is crucial for supporting life. It contains the minerals and nutrients necessary for various ecosystems, and its topmost layer, the soil, is vital for plant growth. The crust's interaction with the atmosphere, hydrosphere, and biosphere creates the conditions necessary for life as we know it. In summary, the Earth's crust is a dynamic, complex layer with a rich geological history. It encompasses the continents and ocean basins, playing a fundamental role in plate tectonics and surface processes. Understanding the crust is essential for comprehending Earth's past, predicting geological events, and appreciating the intricate workings of our planet. The Earth's mantle, a thick layer lying beneath the crust and above the core, is a realm of profound mysteries and immense significance in the planet's geological functioning. Comprising about 84% of Earth's total volume, the mantle extends to a depth of about 2,900 kilometers. It is composed of silicate minerals rich in iron and magnesium, differing significantly in composition and properties from the overlying crust. Unlike the rigid crust, the mantle behaves as a semi-solid, slowly flowing layer. This flow is driven by the heat from the core, causing convection currents in the mantle. These currents are responsible for the movement of tectonic plates on the surface, a process central to Earth's dynamic geology, leading to phenomena like earthquakes, volcanic activity, and mountain formation. The mantle is divided into the upper and lower mantle, each with distinct physical and chemical properties. The upper mantle, which includes the asthenosphere, is partially molten and more plastic in nature, facilitating the movement of tectonic plates. The lower mantle, in contrast, is under immense pressure and is more rigid, though it still flows slowly over geological time scales. The boundary between the mantle and the crust is marked by the Mohorovii discontinuity, commonly known as the MOHO. This boundary is characterized by a change in seismic wave velocities, indicating a transition in rock composition and properties. Despite its inaccessibility, scientists have been able to study the mantle through indirect means. The analysis of seismic waves generated by earthquakes has been instrumental in understanding the mantle's structure. These waves travel through the Earth and are bent or slowed down depending on the material they pass through, providing clues about the mantle's composition and behavior. Moreover, the study of mantle xenoliths, fragments of mantle rock brought to the surface by volcanic eruptions, has provided direct evidence of the mantle's composition. The study of these rocks has revealed much about the processes occurring deep within the Earth. In addition to its geological role, the mantle is also significant for its role in the Earth's thermal history. The heat that drives mantle convection comes from the decay of radioactive elements, a process that has gradually cooled the Earth over billions of years. In conclusion, the Earth's mantle is a mysterious and dynamic layer, playing a crucial role in the planet's geology. Its movements drive the surface tectonics, shaping the Earth's landscape and influencing natural events. Understanding the mantle is key to unraveling the secrets of Earth's past and present and predicting future geological phenomena. The Earth's core, residing beneath the mantle, is a realm of extreme conditions and profound significance in the planet's structure and dynamics. This innermost layer, composed primarily of iron and nickel, is divided into two distinct parts: the outer core and the inner core. The journey to Earth's center reveals a world of intense pressure, high temperature, and complex processes that influence the entire planet. The outer core, extending from about 2,900 kilometers to 5,150 kilometers below the surface, is a sea of hot molten metal. This liquid layer is crucial for generating Earth's magnetic field. The movement of the molten iron in the outer core, combined with the planet's rotation, creates a dynamo effect, producing the magnetic field that shields the Earth from harmful solar radiation. This magnetic field also gives rise to phenomena such as the auroras. Deeper still lies the inner core, a solid sphere with a radius of about 1,220 kilometers. Despite the immense heat, which is comparable to the surface of the Sun, the core remains solid due to the extraordinary pressure at this depth. The inner core is believed to be growing slowly as the Earth cools, with the solidification of the outer core material. The properties of the core are primarily understood through the study of seismic waves. As these waves travel through the Earth during earthquakes, they are altered by the materials they encounter, allowing scientists to infer the composition and state of the core. The different behaviors of seismic waves in the inner and outer core provide evidence for the distinct liquid and solid layers. The core's role extends beyond its contribution to the magnetic field. It also plays a part in Earth's thermal balance. The heat from the core drives mantle convection, a process that is instrumental in plate tectonics. This flow of heat from the core to the surface is a fundamental aspect of the planet's geology. Understanding the core is also crucial for insights into the Earth's formation and evolution. The distribution of elements and the dynamics within the core hold clues about the early processes that shape the planet. In conclusion, the Earth's core is a fascinating and complex region, essential to many of the planet's fundamental processes. From generating the magnetic field to driving plate tectonics, the core's influence is felt throughout the Earth. The study of this deepest layer continues to challenge scientists, offering insights into the planet's past and present, and shaping our understanding of Earth's place in the solar system. Unraveling the secrets of Earth's interior is a formidable challenge, given the inaccessibility of these deep regions. Despite this, scientists have developed ingenious methods to probe the mysteries hidden beneath the surface, enhancing our understanding of the planet's structure, composition, and the dynamic processes that drive it. Seismology has been a crucial tool in this endeavor. The study of seismic waves generated by earthquakes allows scientists to infer the properties of Earth's internal layers. These waves travel at different speeds and along different paths depending on the material they pass through. By analyzing the arrival times and characteristics of these waves at various locations around the globe, seismologists can construct a picture of the Earth's interior. Another window into the Earth's depths is provided by the study of volcanic materials. Eruptions bring to the surface rocks and minerals formed deep within the mantle and crust. By analyzing these materials, geologists can glean information about the conditions and processes occurring at great depths. The study of Earth's magnetic field also offers clues about the inner workings of the planet. The geodynamo, driven by the movement of molten iron in the outer core, generates the magnetic field. Variations and reversals in this field over time have provided valuable information about the behavior of the core and the history of Earth's geology. Advances in computational modeling have allowed scientists to simulate the conditions and processes within the Earth's interior. These models integrate data from seismology, mineral physics, and geochemistry to provide a more comprehensive understanding of the dynamics of the core, mantle, and crust. Satellite measurements have also been instrumental in studying the Earth's interior. Technologies like gravity recovery and climate experiment (GRACE) satellites measure minute changes in Earth's gravity field, which can be caused by the movement of mass within the planet. These data have been used to study phenomena like the shifting of tectonic plates and the depletion of aquifers. Exploring the Earth's deep interior is not only about understanding our planet's past, but also about predicting its future. Knowledge of the Earth's interior helps in assessing geohazards such as earthquakes and volcanic eruptions, and in understanding long-term climate changes and the geodynamics that shape the Earth's surface over millennia. In conclusion, unveiling the secrets of Earth's interior is a multidisciplinary effort, employing advanced technologies and innovative scientific approaches. The information gleaned from these studies is vital for understanding the Earth as a dynamic, evolving planet and for preparing for the geological challenges it presents. Understanding the Earth's interior has profound implications for life on the surface. The dynamic processes occurring deep within the planet are fundamental to shaping the environment in which life exists and evolves. These processes influence various aspects of the Earth, from its magnetic field to geological activities like volcanism and plate tectonics, which in turn affect the climate, landscape, and the very nature of life itself. The Earth's magnetic field, generated by the molten outer core, is crucial for sustaining life. It acts as a shield against harmful solar wind and cosmic radiation, protecting the atmosphere and ensuring stable conditions on the surface. Without this protective field, the solar wind could strip away the atmosphere, as it likely did on Mars, making Earth inhospitable for life. Plate tectonics, driven by the movement of the mantle, play a critical role in the carbon cycle, a key process that regulates the Earth's climate. The movement of plates leads to the formation of mountains, which through weathering, draw carbon dioxide out of the atmosphere. The subduction of tectonic plates carries carbon back into the Earth, a process that helps regulate global temperatures over geological timescales. Volcanic activity, another consequence of the Earth's internal processes, has both immediate and long-term effects on life. Volcanic eruptions can impact climate by releasing large amounts of ash and gases into the atmosphere, sometimes leading to cooler global temperatures. On the other hand, volcanic soils are often very fertile, supporting rich ecosystems. The study of the Earth's interior also offers insights into the origins of life. Hydrothermal vents on the ocean floor, fueled by heat from the Earth's interior, are believed to be among the potential sites where life might have originated. These vents provide energy and nutrients, creating unique habitats teeming with life. Moreover, the internal heat of the Earth, a remnant of its formation and sustained by radioactive decay, drives the geothermal activity. Geothermal energy is a clean, renewable resource that can be harnessed for human use, offering a sustainable alternative to fossil fuels. In conclusion, the workings of the Earth's interior have a direct and profound impact on life on the surface. From regulating the climate and shaping the landscape to protecting the planet from solar radiation, these internal processes are integral to the sustainability of life. Understanding these processes is crucial not only for comprehending Earth's past and present, but also for preparing for future challenges and harnessing the opportunities they present.